So we have an example problem here. We have a projectile is shot straight up from Earth's surface at a speed of 10,000 kilometers per hour. How high does it go? Now we are assuming here the Earth has no rotation, because technically the Earth's rotation does affect the launching of a projectile, but we'll leave that for your dynamics course later. All right, so we have an initial speed of 10,000 kilometers per hour. So this is traveling really fast. A kilometer is 1,000 meters. An hour is 3,600 seconds. So 2,778, that's rounding it to a whole number, meters per second. So we're talking good 6,000 miles per hour. So I would expect this projectile to go far, meaning I expect it to travel farther than the region where we can still assume the acceleration due to gravity is just 9.8. All right, so I'm gonna, draw a rough little sketch. Here's the Earth. We have the projectile, it's launched. So it's gonna travel out to some final location where, just like tossing a ball in the air here on Earth, I am gonna just assume that it's gonna slow down and stop, turn around and come back. So we have an initial R value, which would be the radius of the Earth, which we can pull that off the test notes. We have a final R value, which is essentially what we're looking for. Now, really it wants to know how high it goes, so it's looking for the distance from here to here. So how high it goes will be our final minus the radius of the Earth. Now, energy is a great way to go. So at this initial moment in time, the kinetic energy and potential energy this projectile has together, this energy total, has to still be energy final. Now again, we have to use the negative GMM over R for the potential energy because we're dealing with large distances from the Earth. Now, V final is 0. We expect it will slow down. This projectile is going to slow down, split second it will stop and then come back. And so our equation simplifies a little bit because that final kinetic energy term goes to 0. Now, one other thing that happens when we are equating the energy initially and finally is that the mass of the projectile is canceling out because it is in every term. We're talking about the energy conservation of the projectile itself. So when we equate the initial energy to the final energy, that mass is in every term. So right now, we have 1/2 V initial squared minus GM over R initial is equal to negative GM over R final. The initial speed we have, and we did need to convert that to meters per second. Capital G is our constant, which we can get from the test notes. Capital M is the large object, the Earth. So the mass of the Earth, I would pull off the table in the test notes. Our initial is the radius of the Earth, which I can pull that off the test notes as well. And so my only unknown in here is our final. So what I need to do to isolate our final is I need to do some cross multiplying. Our final will equal negative gm over 1/2 the initial squared minus gm over our initial. So plugging in my values, we can solve for our final. Just got a negative answer, so I need to try again. Plugging these numbers in is definitely a challenge. Okay, so our final, if I have plugged these numbers in correctly, now again, I don't know anything this accurately, but just to write something down at the moment, h, the actual how high it goes above the surface of the Earth, we need to subtract off the radius of the Earth. So I'm getting 4.2 times 10 to the 5th meters. So it goes pretty high. Now, of course, setting the mechanical energy initially equal to the mechanical energy finally is also making the assumption that there's no air resistance, which would certainly not be the case. But it gives us a somewhat of an idea of how far the object can go. So even though this particular object, this projectile, is not in orbit, we can still use that orbital energy equation simply because we're just conserving energy. The potential and kinetic energy initially is still potential and kinetic energy finally. The reality of things, accounting for air resistance, for drag, we also would account for the continual firing of the rockets, because the projectile wouldn't instantaneously have that 2,778 meters per second velocity. So a lot more goes into this, of course. But for our intents and purposes, we're going to just conserve the mechanical energy.